And today we will start with the design procedure for shear with inclined stirrups. Now, inclined stirrups, as we have already discussed, they are slightly different from the vertical stirrups, wherein inclined stirrups have an inclination with the longitudinal axis. They are inclined, they don't stand vertically. Normally this inclination is kept around 45 degrees. So they are inclined, they are tied at a different position on top and at a different position down, not like the vertical stirrups where they are tied vertically on the hanger bars on top and the main reinforcement or the longitudinal reinforcement at the bottom. Now let us look at the design procedure for shear with the inclined stirrups. The procedure more or less remains similar to the procedure for design for shear with vertical stirrups, only with a small or a minor change. Rest of the procedure remains the same. Now what happens? Over here, as for the design procedure for shear with vertical stirrups, as in that case, in the design for shear with inclined stirrups too, the design is carried out after the design of beam for flexure is completed. That means we have already designed the beam, we already know all the parameters such as small b, that is the width of the section, the effective depth, the overall depth, what is the grade of concrete, what is the grade of steel, the amount of steel which has been provided in flexural tension, the loads coming on the beam, the effective span, also whether the beam is simply supported, cantilever, it's a overhang, it's a continuous beam, everything, all these parameters are known. Most important is that the longitudinal reinforcement has already been calculated. We have already calculated the one which we are providing as longitudinal reinforcement, not only what is required but what is being provided. So when we are doing the design procedure, design for the shear with inclined stirrups, first we calculate the value of the ultimate load which is coming over there at that particular section, which creates that shear. Okay, it can be termed upon as ultimate shear force or the ultimate reaction, because we have seen that this is maximum at the support. The shear force is maximum at the support. So that reaction V multiplied by the load factor, which is 1.5, gives us VU. Having calculated the value of VU, that is the ultimate shear force which is coming on the section. Please note, this is the ultimate load which creates the worst shear force in the section or the ultimate shear force. We calculate the value of nominal shear stress. This has already been given in the code on page number 72 of IS code 456 2000. On page number 72 this has already been given. So tau V, we are calculating it as VU upon BD, where VU we have already found out in the previous step as the ultimate shear force. B is the width of the section, D is the effective depth of the section. Having got the value of the nominal shear stress tau V, the next step is to find tau C max, the maximum shear stress the concrete can take before crushing. Beyond this, the concrete would crush. So the value of maximum shear stress the concrete can take, that is tau C max, is directly given to us in table 20 on page number 73 of IS 456 2000. So over here in the table 20, the grade of concrete is given and the value of tau C max has been given. Please note that these values have been obtained over here by the IS code and they have been already tabulated and given, so we don't have to calculate these values. Having done this, we go to step number 4. In step number 4, we compare tau C max and tau V, the maximum value of shear stress the concrete can take before crushing and the nominal stress which is coming on the beam. We compare this. If the nominal shear stress coming on the beam is more than the crushing strength, that is the beam would get crushed because of this, because its own shear capacity of concrete is less, then we need to redesign the section. That is as in the case of the design with vertical stirrups. If tau C max is less than tau V, we need to redesign the section. If in case tau C max is greater than tau V, that means we know that it is safe to continue with the shear design. We continue with the design for shear. Then we find the value of tau C. In that case, what is the value of its own shear resisting capacity of concrete itself. So what is its own capacity now, given that the reinforcement is this much? So for that we need to consider how much is the area of the tension still provided, and it continues for at least one effective depth further, 1d length further than the section considered. So that has been given over there. So we have to consider that reinforcement, that is considered as AS. Now when we look at this table, table number 19 given on page 73 of the code, it is 100 AS upon BD. Now this is the AS which we are considering, and B is the width and D is the effective depth. So depending upon the value, we get the type of we get the value of tau c. Suppose the value comes in between, suppose it is in between 0.25 and 0.50, say it is 0.4, then in between these two values, say it is M20, then in that case in between these two values and these values at 0.4, at 0.40, we need to interpolate, considering that this is a straight line variation, and then we can get the value of 0.4 value, what exactly, how much is the value of tau c. So we calculate the value of tau c by interpolation from this particular code. Those who don't want to follow the table, there are prescribed formulae based on which this answer can also be obtained. So this has been given in the explanatory code of IS 456. Further step than this, once tau c is found out, step number 6 is compare tau c and tau v. Compare its own capability of resisting shear, that is the capability of the beam to resist shear, and how much tau v or nominal shear is coming on the beam. Now if tau v, the nominal shear stress, is less than tau c, is less than its own capability of resisting shear, provide minimum reinforcement as per the IS code given in 26.5.1.6 clause on page number 48, that is ASV upon B into SV is greater than or equal to 0.4 upon 0.87 Fy. So based on this we will be getting the minimum shear reinforcement, and then we have to follow the next clause, that is 26.5.1.5, wherein the maximum spacing of shear reinforcement has to be limited. So over here it says it shall not be exceeding D, the effective depth D in case of the inclined stirrups, and in no case it will be more than 300 mm. So having known this, we will be designing the inclined stirrups. Now this was if tau v was less than tau c. Now what if tau v is greater than tau c? That means the nominal shear stress coming on the beam is greater than tau c, is greater than its own capability. Now in this case, as we used to design with vertical stirrups, over here also assume the diameter of the shear reinforcement, shear stirrups to be provided, and assume the number of legs for the stirrups. Now calculate the VUS, the VU, the shear force which is to be resisted by the shear stirrups, VUS, which is equal to the ultimate shear force coming on the beam minus its own capability, that is tau c into BD. Having got the value of VU, calculate ASV. Now ASV is the area of shear reinforcement, area of the shear stirrups resisting shear. So it is two legs and the circular area. So that area ASV we calculate. Once we have got that, then we look at this formula. VUS is already known to us, Fy is already known to us, ASV is calculated over here, D is the effective depth, alpha, this generally is kept at 45 degrees. Though the inclination is always a subject matter of the engineer who is deciding this, okay, but normally it is kept at 45 degrees, and having known this, we will be getting the value of SV. So the spacing of the inclined stirrups from the shear point of view is calculated. We get the value from this equation. Now this equation has been given on page number 73 of IS 456 2000. So having got this, then we have already calculated this. So this was clause 40.4a on page number 72-73. Once we have done this, we as in the previous case, we give the check for provision of minimum shear reinforcement, that is, and the maximum spacing, what we have seen this. So this has to be done even after doing this check. After doing this check, having got the spacing of the vertical stirrups, check for minimum shear reinforcement and the maximum spacing. Now the spacing will be the least of the spacing obtained here, and the spacings obtained here. The least of them, that would be the spacing considered for the, or spacing taken provided for the shear stirrups. That is what is going to be the design procedure for shear with inclined stirrups.